All right, here we go. Unit 1, Lesson 8, take like 500. You guys have no idea. Limits at infinity, with an emphasis on that word at, because today the objective is to distinguish between infinite limits and limits at infinity. You got to listen carefully to the distinction between those and to evaluate limits at infinity analytically. We'll start off where you might expect. What is that difference? We are familiar with both of these. I just want to make sure we're starting to really be careful about what we say here. An infinite limit, sometimes called a limit to infinity, we're talking about our vertical asymptotes. We're talking about those limits where x is approaching some value c, positive or negative, and the answer to that limit is either positive or negative infinity. So we're talking about, right, x approaches some value c, it heads up to infinity without touching that value c, or it heads down to negative infinity. Those are infinite limits. In the case of f of x on the right, we've got a vertical asymptote at x equals 2. We can see that the limit as x approaches 2 from the left is negative infinity, while the limit as x approaches 2 from the right is positive infinity. And so these are always going to be in the form equals positive or negative infinity. With g of x, same thing. The limit as x approaches our vertical asymptote of -1, that limit from the left is also negative infinity, and that limit from the right is also positive infinity, just like with f of x. We'll review that briefly, but what we're really focusing on today are limits at infinity. We're talking about end behavior. We're talking about what is happening to our function as x approaches either positive or negative infinity. And I'm going to leave this hanging here because this can be either a real number if we're approaching a horizontal asymptote, or it can also be infinity, as you'll see with g of x. Let's first look at f of x. The limit of f of x as x approaches infinity. Infinity means we're heading forever to the right. We're heading closer and closer and closer to that horizontal asymptote of 2. Same thing's happening as we approach negative infinity. The limit of f of x as x approaches negative infinity, we are also heading towards 2, just from the other direction, just from below instead of from above. So you can have these limits equal c, some real number, but they don't always have to. So if you look at g of x, as x approaches infinity, yes, we're approaching an asymptote, but it's not a horizontal one. It's also upward sloping. And so g of x continues to increase as x heads to infinity. G of x also heads to infinity. Heads there more slowly because the slope is less than 1, but it's still heading towards infinity. Versus if x heads towards negative infinity, g of x is also heading towards negative infinity. So limits at infinity can be either horizontal asymptotes, or they can be heading towards infinity or negative infinity. And we're going to be focusing on these limits at infinity today. Even though we're focusing on them, I do want to do a quick review so you can tell the difference between what you would be asked to do analytically, meaning if you didn't have a graph to look at. Key points on infinite limits. We know what they look like from above. They yield vertical asymptotes, and they have non-removable discontinuities. So let's say you saw this on the AP exam and you said, oh, that screams factoring. I'm not even going to try direct substitution because I bet this will factor. And so you say, this is equal to the limit as x approaches 1. This is an equivalent form. 2x plus 1 times x plus 3 over x plus 3 times x minus 1. Did that so quickly because this is, I swear to God, take like 312. The x plus 3's will cancel out. You're going to have a removable discontinuity at -3. So you'll have a hole at -3, but you're not going to be able to get rid of that discontinuity at 1. It is non-removable. If you plugged in 1, you're going to be dividing by 0. And so this tells us right off the bat what we are going to have here is we are going to have a vertical asymptote at x is equal to 1. And the question just becomes, is this a vertical asymptote where we're approaching infinity or negative infinity? And so the trick here is the following. The trick here is to say, okay, let me look at 2x plus 1 over x minus 1. Let me first imagine that x is 1.1, just slightly to the right. We'd have 2 times 1.1 minus 1 over 1.1 minus 1. Now, I don't even really care what these numbers are. What I care about is that this is a positive number divided by a increasingly smaller positive number. 1.01 minus 1 is going to be 0.01. Then going to be 0.001. The denominator is getting smaller and smaller and smaller, but it's still positive. Positive divided by positive is positive. So as we approach from the right, this value is approaching positive infinity. Versus from the left, let's call this, say, 0.9. We'll have 2 times 0.9 minus 1. That's still a positive number. Over 0.9 minus 1. Now we're talking about a negative number. So as we get closer and closer to 1 from the left, like 0.9, we're heading towards negative infinity. And so that's the analysis that I would want you to do for finding vertical asymptotes, for finding infinite limits. Now, quick preview here. What's the limit at infinity going to be? What's this end behavior? I'll humor you, right? This is eats DC because the x squared terms dominate. As x goes to infinity, nothing else matters but those x squared terms. And the x squared terms, once everything else is gone, then they will cancel, and you'll just be left with the limit as x approaches infinity is 2. So what we're going to have here is a horizontal asymptote at 2. But the idea here, just to wrap this up, this limit does not exist as x approaches 1. Doesn't exist under any textbook definition because we're going opposite directions. I have to do this backwards in the mirror. We're going opposite directions, one way to positive infinity, one way to negative infinity. Let's get really formal about limits at infinity. They describe the end behavior of a function. So throwback to Algebra 2, when we said things like as x approaches infinity, really we were talking about limits, we just didn't have the language to describe it yet. So we had that whole roller coaster project. What's happening to negative 5x cubed plus 50x squared plus 5 as x heads to infinity? The important piece of information here is that the highest degree term will dominate. If you're plugging in really big numbers to x, yes, the x squared term has a 50, but if x is big enough, the x cubed is going to be way bigger than 50 anyway. So what matters is what's happening to the highest degree term. So nothing that happens besides that x cubed is going to matter. And I like how delta math does this. They say, okay, the limit as x approaches infinity, to help think about it, they write negative 5 times, they literally write the word big cubed. Well, a big number cubed is still a big number cubed. So this is negative 5 times a big number, right? You can also think of this as negative 5 times infinity. So what we have here, the limit as x approaches infinity of this function is negative infinity. And spoiler, we've got it graphed here. Yes, that's true. Our end behavior clearly shows we're heading towards negative infinity. Versus, same thing, we'll apply that delta math logic, right? These things don't matter. This is going to be negative 5. Now we're plugging in negative infinity. So we're going to say a negative big number cubed. Now you have to kind of do the finger counting thing, right? Or just know odds and evens. A negative big number times a negative big number is a big positive number times another negative big number, you're back to negative. So this is negative 5 times a negative big number. This is positive big number or positive infinity. Big number, infinity, same thing. Just I thought it was funny. So you can use that for your notes. And it also just feels weird to plug in infinity to things. So that's end behavior, right? Where this gets tricky is where we have rational functions. Rational meaning ratio, meaning fractions. And so we're going to go through just a few examples of how to deal with this when we have rational functions. Each time I will humor you with Bobo needs DC, but it'll be the last time I ever say it. So case number 1, the denominator is of a higher degree power. I keep saying that degree term because, again, what I'm saying is as x goes to infinity, Negative 4x cubed is going to be way bigger than 2x squared. It's going to be way bigger than negative 4. 5x to the fourth is going to be way bigger than 2x cubed. It's going to be way bigger than 3x. The reason I like to show those crossing off is now you can just imagine that what we have here is negative 4x cubed over 5x to the fourth. Well, 3 of those x's are going to cancel now. So we're going to have negative 4 over 5x. If x heads to infinity, what's happening here is negative 4 over a bigger and bigger and bigger number. We are heading towards 0. So that's your Bobo, bigger on bottom. The asymptote is 0. That is the logic for that, is because as x heads towards infinity, the 5x to the fourth on the bottom, that's the dominant term. And it doesn't matter whether it's negative or positive infinity. In either direction, we're heading towards 0 here, as you can see on the graph from the left. The limit as x approaches infinity is 0. The limit as x approaches negative infinity is 0. Case number 2, the numerator is of a higher degree or power. So let's say we had 6x to the fifth minus 2x squared minus 4. Same thing, cross off what doesn't matter. We have 6x to the fifth on top, 50x squared on bottom. This is going to be 6x to the third over 50. You start to see these really quickly. As x heads to infinity, we are heading towards infinity here. The one you have to be really careful about is with negative infinity. This one, it's worth taking a second to say, okay, 6x to the third over 50. That's 6 times a negative big number cubed over 50. Negative to the third power is still negative. So we've got negative big number over 50. You get the point. It's negative infinity. All that matters is the sign. This is your Botan. Bigger on top, no asymptote, I think is what that means. This is another reason why I'm not a fan of Bobo, Botan, HTC, because I don't just care that there's no asymptote. I care about what's happening. I care about, am I heading to positive infinity or negative infinity? Finally, the last one, the numerator and denominator are of the same degree. So let's take a look at this example. If we have the limit as x approaches infinity, I see that as x approaches infinity, I start crossing off. All that matters is 8x cubed over 2x cubed. X, yes, it's heading towards infinity, but it's the same infinity. So it's like 8 times 10,000 cubed over 2 times 10,000 cubed. The x cubes will cancel at this point once the others are irrelevant. Once the others are irrelevant, it's just like you had 8x cubed over 2x cubed. The x cubes will cancel. You have 8 over 2 to make 4. So the limit as x approaches infinity is positive 4. Same thing is going to happen on the right. The irrelevant terms will cancel. 8x cubed over 2x cubed equals 4. That's your EATS DC. I honestly can't even remember what that stands for, but the idea is as x heads towards infinity, only the leading degree term, the highest exponent, matters. And once you've crossed those other ones off, our same cancellation rules apply. The x cubes will cancel each other out, and you'll be left with 8 over 2 to make 4. So both of these limits are 4. Let's go ahead. Oh, there it is, EATS DC. Who knows what that stands for? Let's go ahead. Let's try some of these out. Man, my formatting got all weird, but here you go. Try this out. What is the limit as x approaches infinity of negative 6x squared times 4x squared minus 3 over x cubed minus 10 times 7 minus 4x? Okay, so what I think might have happened is you might scan this picture and you might say, okay, x squared's on top, x cubed's on bottom, bigger on bottom. I think what I'm expecting a lot of people to say here is 0. You have to do all of your algebra analysis before you determine what the limit at infinity is. In this case, if you were to distribute, you'd have negative 24x to the fourth plus 18x squared on the top. On the bottom, I'm going to show you a little trick to save some time. Yes, I could do first, outer, inner, last. I could distribute. I could do that binomial multiplication. But all I really care about is that leading term. So all I care about is what is x cubed times negative 4x. it is negative 4x to the fourth. I don't have a dot, dot, dot here. We're going to have some more terms, but I write dot, dot, dot because key point for today, only the leading term is going to matter. Who cares what they are, as long as you make sure you've identified the leading one. We actually have an eats DC problem here because we have the same highest degree once we've done all of our multiplication out. So these x to the fourths will cancel. Negative 24 over negative 4. We are going to have an asymptote of positive 6. So whatever else is going off on this graph, as x heads towards infinity, maybe it looks like that, maybe it looks like that. The idea, what I care about today is that as x heads towards infinity, the limit as x heads toward infinity is 6, not 0, as a quick glance of the exponents might have led you to believe. So key point, you have to think in terms of final degrees. So try to apply that, but apply it to this one. The limit as x approaches infinity of the square root of 49 plus 4x to the sixth plus 4x cubed all over 10x cubed plus 2. All right, so the key point is you have to think in terms of final degrees. This one's trickier. One thing you can do, right? We do know, since the only thing we have here is a square root, the 49 is not going to matter. The 4x cubed is not going to matter. We can take the square root of 4x to the sixth power, right? It's what thing times itself is 4x to the sixth. This is going to be 2x cubed, because 2x cubed times 2x cubed is 4x to the sixth over 10x cubed plus 2, right? But that doesn't matter. We have another eats DC problem. After you take the square root, they both have a highest degree of 3. X to the thirds cancel. 2 over 10. The limit as x approaches infinity here is 1/5. So just again, that key point, you have to do all your distribution out or do your roots before you think about what that highest degree term is. We're going to end on 2 real AP questions. So let's start off with this first one. What is the limit as x approaches infinity of 2x minus 1 times 3 minus x over x minus 1 times x plus 3? And yes, this is a real AP question, right? And you only need to get a third of them right to pass this test. So I hope you're starting to feel pretty good about yourselves. All I care about is the highest degree exponent. So I don't need to do, you can if you want, you can do all this multiplication out, but all I care about is that on top, the highest degree is going to be negative 2x squared, and then some other stuff that's not going to matter. On the bottom, the highest degree is going to be x squared, and then some other stuff that I don't care about, because as x heads towards infinity, only the highest exponent will matter. We have an eats DC, the x squareds will cancel. The limit as x approaches infinity is -2 when we divide those coefficients. Now, if it makes you more comfortable, multiply the whole thing out. This is definitely like a way you could make a mistake, but once you've done enough of these, you see on the top, we're gonna have -2x squared and some other stuff that doesn't matter. On the bottom, we're gonna have x squared and some other stuff that doesn't matter. And I actually like that you think of it that way because it shows an understanding that as x approaches infinity, the highest exponent term is going to dominate. Last one here. The line y equals 5 is a horizontal asymptote to the graph of which of the following functions? All right, so what we're looking for here, the line y equals 5, we are looking for a horizontal asymptote, which means we're looking for which of these functions as x heads towards infinity or negative infinity is the limit equal to 5. All right, sine of 5x over x. As x heads towards infinity, sine is going to just bounce up and down between 0 and 1. X is going to head towards infinity. This is a bobo, right? This is bigger on bottom, right? This is why I don't like bobo, because you really need to think about just what dominates. And x is going to dominate here, so it's not A. For B, as x heads towards infinity, 5 times x also heads towards infinity, not B. Y, or C, as x heads towards infinity, infinity minus 5, this is 1 over infinity. That's a Bobo, right? Heading towards 0. Let's see this last one. D. Now, D is interesting. 5x over 1 minus x. So all that's going to matter here is that we're doing 5x over negative x. What we're going to have here is the x's will cancel. We'll have 5 over negative 1. This function will head towards negative 5, not positive 5, which leaves us with final as x heads towards infinity. So what this problem is really testing is, do you know that this term horizontal asymptote means the limit as x heads towards infinity? As x heads towards infinity, the negative x won't matter. The 1 won't matter. We'll have 20x squared over 4x squared. I'm so excited because I'm actually going to nail this take. X squared over x squared cancels out. 20 divided by 4 is 5. There you go. Final answer is E. You'd have about 2 minutes to do these problems, right? And so a lot of it is just like these beginning limits. One can be pre-cal understandings. Remember, limits at infinity mean you do your pre-cal Bo needs DC analysis. You don't tell me that's what you were thinking in your head. You tell me that what you were thinking in your head is the leading degree terms will dominate, and I thought out what would happen from there in terms of limits. But you can use that knowledge to help you get there.